Greetings. Welcome to the second lecture on electronic circuits. I am Razavi. Today we will continue to look at the semiconductor physics and how we need to understand the concepts in building devices so that eventually we can construct various interesting electronic components. But before we start, I would like to give you a quick review of the first lecture just to prepare us for today's concepts. So here's a little board summarizing what we learned last time. We started by looking at the structure of an atom, and we said that the outermost shell contains electrons called valence electrons that might be freed if they obtain enough energy. And we saw that, for example, silicon has 4 electrons in the last orbital. Now, we said that if we arrange silicon atoms regularly in a crystal form, as shown here, then each silicon atom will share 4 electrons with its neighboring atoms. And they seem perfectly happy. Each of them has completed its outermost shell by sharing these electrons. And we say that these atoms have formed a covalent bond. Now we saw that at a finite temperature, the bonds may be broken if an electron has enough energy from the environment, let's say thermal energy, so that it breaks free from the bond. And the equation that tells us how many free electrons we have in a cubic centimeter of the material is given by this expression, which contains the band gap energy of the material. For example, for silicon, the band gap is 1.12 electron volts. Now, if we calculate this at the room temperature, we see that we have about 10 to the 10 free electrons per cubic centimeter. And that's not a whole lot, considering that a cubic centimeter of silicon has something like 10 to the 25 atoms. So we have very, very few electrons. In other words, the silicon is not pure silicon is not a very good conductor, and we need to modify somehow the number of free electrons that we have. The next concept we talked about was holes. We saw that every time an electron is knocked out of a bond, it leaves behind a void that could absorb an electron, and that void is called a hole. So we say that we have created an electron-hole pair every time there's enough energy to release one electron from the bond. And what we see is that the number of free electrons per cubic centimeter is equal to Ni, that expression, and so is the number of holes because they are created simultaneously. So please remember these two and the fact that they are equal to Ni in pure silicon. All right. Now, given that we don't have that many free electrons, we see that silicon has a relatively high resistance. It's not a very useful material by itself. So we're thinking perhaps there's a way to modify the density of electrons and holes in silicon. And what we discussed last time was perhaps we can try to add some impurities to silicon. And if we go back to the periodic table, we see that in column 3 we have boron. So boron has 3 electrons in the last orbital, whereas silicon and germanium have 4 and phosphorus has 5. So for example, if I go into a silicon crystal and replace some of the atoms by phosphorus atoms, then this phosphorus atom has 1 additional electron that cannot form a bond with the surrounding silicon atoms. And that free electron is capable of carrying current. So if we add a certain number of phosphorus atoms to a silicon, a piece of silicon, then we create that many free electrons. And that's what we call doping. So we can increase the number of free electrons in the material by doping, for example, phosphorus. If we do that, we call this an N-type material because now it has more electrons. Also, the phosphorus itself is called the dopant or a donor because it donates electrons for current conduction. All right, so today we will continue the concept of doping. And this is the outline of material that we will cover today. So we will continue talking about doping and reinforce the idea of an N-type semiconductor, as we just saw, and a P-type semiconductor. So we have to see what these mean and how they differ. Then we need to calculate the actual carrier densities, a number of electrons and holes, when we do this type of doping. Do they go up? Do they go down? How do they change? So we need to formulate these because we will need them later. And by then, we have answered the third question that we raised last time, namely, how do we modify carrier densities in a piece of silicon? Now, the fourth question that we raised last time, and now we need to answer is, all right, now we got all this charge available, ready to go. Now, how does the charge actually move in the semiconductor? And we will identify two mechanisms for carrying current. One is called drift, and the other one, diffusion. So we'll talk about these today as well. Okay, so let's begin with doping. And remember from what I just said, that we are introducing impurities inside a silicon crystal to adjust the number of, for example, free electrons that we have. All right, now before we go there, I need to make sure that we understand our notation. The notation can be confusing as we go along, so let's just make that very clear at this point. So we saw that if we add n donor atoms, for example, phosphorus atoms, then we also add n free electrons. Then the density of free electrons is equal to n. Is that strange? It's a little strange because before doping for the intrinsic, for the pure silicon, we already had free electrons. So shouldn't we add these two, Ni, the number of free electrons for the pure silicon, and then this many donor atoms, this many electrons for the addition, for what's contributed by, for example, phosphorus atoms? Well, we are making one assumption here, which is actually very good in practice. The assumption is that the number of donor atoms that we add is much higher than the original free electrons that pure silicon had. Remember, a pure silicon had 10 to the 10 electrons per cubic centimeter. In practice, when we add this, we add something like 10 to the 15 or 10 to the 17 donor atoms per cubic centimeter. So this number is so much higher than the original Ni that with a very good approximation, we can say the number of free electrons per cubic centimeter is n. Okay. Now, the only confusion which we will face later is that we may have other types of impurities that we are adding, and if we keep calling all of them n, then we don't know which one is which one. So we will add a subscript, Nd, for donor. So Nd is the number of free electrons per cubic centimeter. So I will write per cubic centimeter. Okay, so let's remember that. All right. Now, the number of free electrons per cubic centimeter is some amount. The number of holes per cubic centimeter is also some amount. In pure silicon, these two were equal, if you remember, because for every electron that was released from a bond, we also had a hole. Now, is that true here? We add some donor atoms, so we have lots of free electrons. What happens to the holes? Do they stay the same as pure silicon? Do they go up or do they go down? So we don't know yet, but there's also room for confusion in terms of our notation. So to make sure that we're not confused, we will also introduce the following notation. So we'll say n, little n, is density of free electrons. And P, lowercase p, is density of holes. Now, of course, for pure silicon, this and this were equal and equal to Ni, as we saw before. So for intrinsic silicon or pure silicon, we have N is equal to P is equal to Ni. For every electron that was released, we had a hole, so these two are equal and equal to Ni. But now that we have added some impurity, things become interesting. We know that N has gone up considerably. It was 10 to the 10, now it's some amount, maybe 10 to the 15. But what happens to P? Okay, so we don't know yet. But for pure silicon, obviously, if I look at this equation, I can say that N times P is equal to Ni squared. Right? Very simple. But what also turns out to be the case, and we will not prove it here, is that for doped silicon, for example, if it's doped with phosphorus, it is also true that N times P is equal to Ni squared. Strange but true. So this equation plays a critical role in our derivations later. And it's very interesting because it says that the product of the electron density and hole density is always a certain number. It doesn't matter what we are doing to the silicon, we're doping it or not doping it, what type of doping we're using, as long as the crystal structure and is doped or not doped, this product is always equal to a constant value. This is constant, assuming the temperature is constant. Now that raises an interesting question. We just said that if we add Nd phosphorus atoms to 1 cubic centimeter of silicon, we introduce this many electrons, approximately, assuming that Nd is large. So for doped silicon, and more specifically for N-type silicon, silicon that is doped with a donor, we observe that N is approximately equal to Nd. The number of free electrons approximately equal to the number of phosphorus atoms that we added. So far so good, as we said before. But if I go back to this equation predicts something else that's interesting. It says P, the density of holes inside a P-type material, inside an N-type material, is equal to Ni squared over N. So it's equal to Ni squared over Nd. So what does this say? This says that if I take a piece of silicon and we add donor atoms to it so as to raise the density of free electrons by a large amount, so we go to Nd per cubic centimeter, then what happens is that the density of holes actually goes down. It's no longer equal to Ni, it's Ni squared over Nd. Because Ni is about 10 to the 10. Nd is about 10 to the 15. So when we do the calculation, we see that P is very small. Why did the number of holes go down? Well, because we have an abundance of free electrons, and many of these electrons go and fill up those holes. So the number of holes becomes very small. So just to give you a quick example of what we have here, let me do a calculation. So we take a 1 centimeter by 1 centimeter by 1 centimeter piece of silicon. So this is silicon. And what we know is that we add 10 to the 15 phosphorus atoms to that 1 cubic centimeter. Okay, so then what happens? Well, we know that because this is so far above 10 to the 10 for Ni, we can say that N, the number of free electrons, is approximately equal to 10 to the 15, which is what we call Nd. This is per cubic centimeter. How about the number of holes? Number of holes will be, we know that is always equal to Ni squared over N, because this product always has to be Ni squared regardless of whether it's doped or not doped. But in this case, N happens to be just the number of phosphorus atoms. So approximately. So it's Ni squared over Nd. And because this is 10 to the 20, and this is 10 to the 15, we have 10 to the 5 per cubic centimeter. So interestingly, by adding 10 to the 15 phosphorus atoms to 1 cubic centimeter of silicon, we managed to increase the number of free electrons to the same amount. So now it's much more conductive than before, 10 to the 5th times more conductive. So that's a huge improvement in conductivity. But at the same time, the number of holes dropped considerably. It dropped also by a factor of 10 to the 5th. So that's an interesting effect that happens when we perform doping. And then it's not surprising if we come along and we say, I will change the color of my pen to red. It's not surprising if we call for this N-type material, we call this majority carrier, and P, the minority carrier. Minority carrier. So when we perform N-type doping with, for example, phosphorus atoms, we have created, we have made electrons the majority carriers and holes the minority carriers, because now they differ by so much. This is 10 to the 15, this is 10 to the 5. Okay, very good. Now, the next question that we can raise is, can we do the reverse of all of this? By that I mean, can we add something that makes holes the majority carriers and electrons the minority carriers? So for that, we have to look for something other than phosphorus to add to silicon. Because phosphorus had 5 electrons. Upon forming bonds with silicon atoms, it had 1 free electron that was would participate in current conduction. So we should be looking for something in the 3rd column. If you remember from the periodic table section that we saw, the 3rd column had boron in it, B. So what if we take a piece of pure silicon and go in there and substitute some of the silicon atoms with boron atoms? So that brings us to the next topic, which is, can holes become majority carriers? Okay, well, we will form a crystal of silicon, but this time we introduce boron atoms in there. Now boron has only 3 electrons in its last orbital, so it cannot form a complete bond with the neighboring silicon atom. So it will end up using one electron with this, one electron with this, one electron with this, but doesn't have another electron for this silicon atom. So there will be a void here, and that void is a hole because that bond is not completed. So we end up with a hole here. Let me change the color of my pen to brown maybe. Well, brown is... So we end up with a hole here, and that hole is above and beyond the holes that the pure silicon already produced. This is a different type of bond, right? You could knock off an electron here from one silicon atom bonded to another silicon atom. But in this case, this hole is created simply because boron doesn't have an electron to share. So if we add a certain number of boron atoms to silicon, we created that many holes in silicon, in addition to the intrinsic holes that pure silicon had. So it's similar to the case of phosphorus, except that everything is now flipped. Okay, so in this situation, we will call this a p-type material, because now we're hoping that the holes will become majority carriers. So this is what we call a p-type semiconductor. And now we can repeat these equations. So let's say we add n boron atoms per cubic centimeter of silicon. Then we have n holes, approximately, because we still have the holes of pure silicon, but again we're assuming that the number of borons that are added is much more than 10 to the 10. So again, typically it might be 10 to the 15, 10 to the 16, 10 to the 17. Okay, so again, to avoid confusion, we will add subscript A here and here. And A stands for acceptor, because boron, in this case, operates as an acceptor, not a donor. Boron would like to receive an electron and fill up this hole, as opposed to phosphorus, where it would donate an electron. So we call it acceptor concentration, Na. And that means that the number of holes that we have in 1 cubic centimeter is equal to approximately Na. Because Na is so much larger than Ni that it is a good approximation. Okay, so we have created holes, lots of holes, depending on how many boron acceptor atoms we add to the silicon crystal. What happens now to the density of free electrons? Well, because we have so many holes, some of these holes are filled up by the free electrons that pure silicon had. So the number of free electrons goes down, because some of those free electrons go and fill up these holes. They are no longer capable of carrying a current. So we know that N times P is always equal to Ni squared, which is a constant. And we know that P in this p-type material is equal to Na. So that means that N is now approximately equal to Ni squared over Na. So what we see is that the number of free electrons has dropped considerably, just like before, but in reverse order. Okay, so then it makes sense to say that in the p-type material, holes are the majority carriers and electrons are the minority carriers. And this distinction is critical to building interesting semiconductor devices later. Very well. Let me give you a quiz before we continue. What happens to N and P in N-type silicon as temperature increases? So I will give you 90 seconds to think about this. All right. Did you figure out how these concentrations vary with temperature? Well, here's a way to think about it. We have temperature on this axis, and then we're looking for N and P. It's an N-type material. So for N-type material, we know that N is approximately equal to ND, the number of dopant atoms per cubic centimeter. And we also know that P, which is a minority carrier now, is approximately equal to Ni squared over Nd. So the number of free electrons per cubic centimeter doesn't really change much because the number of donor atoms inside silicon is constant. So as a function of temperature, N is approximately constant. How about P? Well, P is proportional to Ni squared. And remember, Ni had a relatively close to an exponential rise with temperature. So what we see is that P increases like this as a function of temperature. So as temperature goes up, the majority carriers are about the same, but minority carriers increase rapidly. So that is the answer. Very well. Let's continue. I would like to summarize everything we have learned about doping before we move on to how current moves, how charge moves in semiconductors. So here's a quick summary. And let me change the color of my pen to maybe this color. See if that works. So summary. All right, so we have seen two types of materials. What we called N-type and what we call P-type. In N-type material, we come along and add donor atoms, for example, phosphorus, with a density of Nd. That means Nd donor atoms per cubic centimeter. In a P-type material, we come along and add acceptor atoms, atoms that have deficiency in the number of electrons. They have 3 electrons, for example, in the last orbital instead of 4. So when they form a bond with the adjacent silicon atoms, we are missing an electron, so we have a hole in there. And this is called Na. All right, so in an N-type material, we saw that N, the density of free electrons available for current conduction, is approximately equal to Nd, because Nd is typically large. So these are on the order of 10 to the 15 to 10 to the 17, whereas the number of free electrons is approximately equal to Ni, number of holes is approximately equal to Ni squared over Nd. So that's what we call majority carriers, and this is what we call minority carriers. Okay. In the p-type material, it's the other way around. So because we have added acceptor atoms, not donor atoms, it doesn't really make sense to add both of them, we have lots of holes. And that means that the density of holes in that material is approximately equal to Na. But many of these holes also go and fill up the free electrons that we had from pure silicon. Remember, 10 to the 10 free electrons per cubic centimeter. So we go fill up some of those. So now N becomes small. N becomes equal to Ni squared over Na. And again, these are majority carriers, holes, and these are minority carriers, electrons. Okay, so we have answered our third question. How do we modify carrier densities in a piece of silicon to adjust its conductivity? We see that in this case, we have raised the conductivity. It's a more conductive material. And the main mechanism of conduction is through electrons. In this case, we have raised the conductivity, but now the main conduction mechanism is through holes. So these have different types of operation. Okay, we are now ready to go and address the fourth question I raised in the first lecture, namely, how do charge carriers move in silicon? So we identify two mechanisms. So this is what we call carrier transport. Carrier transport is another name for charge movement in a semiconductor. Okay, so as I mentioned at the beginning, there are two mechanisms for carrier transport. One is called drift and the other diffusion. So we'll now focus on drift. So we have drift and diffusion. So we will focus on drift. Drift is actually a very familiar effect to us because it comes from applying a voltage or applying an electric field to the material. So if you take a piece of silicon, here's a piece of silicon, doped or undoped, doesn't matter too much, and we apply a battery to it, call it VB, assuming that this is a uniform crystal, we have created an electric field from here to here, right? So there's an electric field oriented this way because we have applied a voltage. And if there's any charge carrier, for example, electrons, these electrons will see the electric field and start moving. So they start moving from here to here. They are absorbed to the positive terminal of the battery. So drift is simply current conduction due to electric field. Nothing dramatically different from what we have seen in basic circuits, basic physics, and all those things. All right, so that's interesting. Our objective is to quantify the current that arises in a piece of semiconductor when we apply voltage to it. So we're thinking maybe Ohm's law. So Ohm's law may apply here. Maybe, maybe not, right? But maybe that's what we should be looking at. So if we can find R for a piece of silicon, doped or undoped, then we're set, because we can just plug it in here, and that will give us the relationship between the voltage and the current. Now, how do we find the resistance of this material? Well, it's a little tricky. If you remember, in basic physics, we found out that the resistance of a given object is calculated as follows. R is equal to rho times L over A. L is the length of the object, so this is L. A is the cross-section area of the object, so A is here, this is A, this area, and rho is what we call the resistivity of the material in that object. So the material could be metal, could be carbon, could be various things. In this case, it happens to be silicon. Okay, so we could try to find rho. If we find rho, then we're set, because these are numbers that we can measure for any object, and then if we know the resistivity for silicon, plug it in here. If we have R, then we have V equals IR, we're all set. We know the relationship between the voltage and the current. Okay, all right, now to find rho, or generally to find the relationship between V and I and R, we have to work a little harder for semiconductors. It's a little different from our intuition and from what we know in the past. All right, so to go there, let me talk a little about what happens when we apply an electric field. Well, we know that the electric field is defined as the force that a unit charge experiences when the charge is placed in that field. So if I take, for example, 1 unit of positive charge and put it over here, or here, or here, or here, doesn't matter, it's uniform, it feels a certain force going that way. Because positive charge wants to go from here to here. This is positive, this is negative. So that's the definition of electric field. Now, if the unit charge experiences a force, then it should accelerate. F equals ma. Should it not? All right, so if it accelerates, it means that its velocity keeps increasing. So how does it work? If we start with a unit charge here, and it's propagating, it's flowing through silicon, does the velocity just keep increasing and increasing, or not? Well, this is reminiscent of when you jump from an airplane in a parachute, with a parachute. What happens? Well, the parachute opens, hopefully, and you come down, and because of the air resistance experienced by the parachute, you will soon reach the terminal velocity. This is something you remember from physics. So if this is your parachute, and you're hanging here for dear life, we know that even though there's gravity this way, there's also air resistance this way, and eventually these two cancel each other, and we end up with a constant velocity. And that constant velocity is called terminal velocity. Now, a similar effect happens in silicon. When the electrons are accelerated by the electric field, there's a counter force, and the counter force is the result of the electrons hitting the crystal of the silicon. Remember that silicon has lots of atoms, and we don't have that many electrons. We have 10 to the 25th atoms per cubic centimeter, but we have 10 to the 15 or 17 or 16 electrons, for example. So there are lots of silicon atoms lying around, and as the electrons try to travel, sometimes they hit these atoms. And when they hit these atoms, they lose some of their velocity. So they do not accelerate indefinitely. They reach a terminal velocity. So then what this tells us is that there is a terminal velocity. There's a velocity for the electrons as they propagate. And intuitively, we would expect that this velocity should be proportional to the electric field. right? The higher the field, the higher the voltage, the faster the electrons should move. So then this should be proportional. This is the velocity of electrons in a semiconductor, should be proportional to the electric field. Okay, so we cannot say V is equal to E because they have different dimensions. This is velocity meters per second, this is electric field, so we can't make them equal. We need a proportionality factor. So we say V is equal to E times something, and that something is called mu n. N stands for electrons, because we have this coefficient for electrons, we also have this coefficient for holes. And then mu sub n is called the mobility, meaning how fast they can move, how mobile they are. So this is called electron mobility. All right? So that's interesting. It says that when we apply a certain electric field, we apply a voltage, we develop an electric field, we have a field oriented from here to here. Electrons start from this side and they're traveling that way. Electrons start from this side and they're traveling this way. And because they experience this electric field and the electric field is uniform, they quickly reach this velocity. And then they just have that velocity as they start from here and travel to the left. And that velocity can be calculated if we know how much that is. Now, mu sub n for electrons is equal to 1350 volt per centimeter times second. Very strange unit. I'm sorry, centimeter. Okay, I made a mistake here. So the unit is centimeter squared per volt second. Centimeter squared per volt times second. That is the mobility of electrons in silicon. All right. Okay, so we have found the velocity of the carriers. We're still far from finding the resistance. That's what we want to find. So we need to make another observation that is extremely useful in calculating current in a semiconductor. So that observation is the following. So let me change the color of my pen and I will go through that observation. So let's go to black this time. Okay, how do we calculate current anyway? Or how do we calculate resistance anyway? Well, one way would be to apply a voltage and measure the current and divide and find the resistance, right? So maybe that's what we should do. Let's take a piece of silicon. So here's a piece of silicon, and we apply a voltage to it. We assume that the length is L, the width is W, and the thickness is H. So this thickness here is H, lowercase h. So we have the dimensions of this piece of silicon, and we are applying a certain voltage. So just like before, we call this VB. Now whether you want to write this as a rectangular prism or as a cylinder doesn't make any difference. It's just the same thing. And we need to find the current. assuming that we know the velocity of the carriers. We know the electric field, we know the velocity of carriers, we want to find the current. If we find the current and we have the voltage, then we can find the resistance. That was the ultimate objective. Okay, so how does this work? Well, the first thing we know is that if we have the voltage and we have the length, we have the electric field, right? So we know that the electric field is equal to VB over L. If you remember, voltage is minus integral of the electric field along the distance. Because the electric field is constant from here to here, we can take it out of the integral, and that just means the electric field is voltage divided by the length. I'm a little sloppy about the signs here, but that's okay, don't worry about it. Okay, so we have the electric field, therefore we have the velocity. How do we relate the current that flows to the velocity of the carriers? Well, here's the interesting observation. The way we calculate current in general is as follows. We will take a cross-section area, we sit at this cross-section, and calculate the charge that passes this cross-section in 1 second. That is the definition of current. All right, so let's go sit here and find all the charge that goes from left to right through this cross-section in 1 second. That would be the amount of current. All right, so how much charge passes through this? Well, we know that there is a charge everywhere. This has some number of free electrons or holes, etc., right? But we also know that the charge moves at the velocity of v. A velocity of v means that the charge moves v meters in 1 second. V meters in 1 second. So if I start from here and I go back v meters, so this distance is v meters, then all of the charge in this volume will pass this cross-section in 1 second. You look at the last charge over here. 1 second later is over here. It has passed. And of course, any charge in between has passed. So all of the charge in this volume will pass this cross-section area in 1 second, and that is the current, because current is defined as charge passing through the cross-section in 1 second. Okay, so what we need to do is find the total charge that we have, the total free charge that we have in this rectangular prism. Okay, so it shouldn't be that hard. This dimension is a V. So total charge is equal to, this dimension is V, this dimension is W, this dimension is H. That's the total volume. Now inside here we have a certain carrier density. Let's say it's an N-type material, so we have N free electrons per cubic centimeter. Okay, is that charge? Is that charge in Coulomb? No, because this is just the number of electrons. You have to multiply it by the charge of each electron. The charge of each electron is Q, so that is the total charge that we have. This is the total charge that passes this cross-section, so that is the current. So this is the current. I'll put an absolute value here, absolute value sign, just to make sure we don't get confused. But this is the total current that passes that cross-section. Total charge that passes in 1 second. Okay, now V is given by mobility times electric field. And electric field is given by voltage over length. So we can say that the current is equal to, instead of V I will write mu E, instead of E I will write VB over L. So I have mu of electrons times VB over L times W times H times N times Q. We have lots of parameters lying around, but that's okay. So that is the total current that passes through this piece of semiconductor in response to a voltage VB. Okay, can we find a resistance? Sure, we have a voltage, we have a current, so everything that's multiplied by the voltage is 1 over the resistance. So we can say that the resistance is equal to L over mu n W H N Q. So far so good? Okay. So this is H, that's N. Is this analogous to our basic equation? L is the same length. How about A, cross-section area? Cross-section area of this object is this here, right? Which is W times H. So W times H is what we called A before. And then the rest, mu n, n, and q form this rho. So we can say that is equal to 1 over mu n, n, q, L over A. So now it's simple. We see that the resistivity of that semiconductor, rho, is equal to 1 over the mobility, the concentration of electrons, and the charge of 1 electron. And that makes sense. If we have a higher mobility, meaning that the devices can have a higher velocity, we have more current, we have less resistance. If we have more electrons to carry the current, we also have a lower resistance. So that makes perfect sense. So we might call this the resistivity of a silicon if its majority carriers are electrons. Okay, all right. So we saw that this was the equation for the current that flows. In practice, in semiconductors, people like to show current density. Current density is a little strange, but that's the common practice, so we will follow that. Current density means the amount of current that is flowing per unit cross-section area. So rather than consider the total current that passes through this, we just take a unit area, let's say 1 micron by 1 micron, 1 meter by 1 meter, 1 centimeter by 1 centimeter, right? Just a little area here and see how much current is passing through it. That's what we call the current density. So remember this equation, and now we will change it to current density. It's not that hard, right? Because if we divide this total current by the cross-section area, then that will give us the current density. The unit of this current is amperes. The unit of current density is amperes per square centimeter or square micron or square meter, whichever we like. So we just divide it by the cross-section area, which is W times H, remember? So we just divide by WH, and that will give us the current density. So the current density will be equal to mu n times the electric field times n times q. So remember that. I'm going to the next page now. So the current density is equal to mobility times the electric field times the density of electrons times the charge of electrons, right? So mobility, electric field, density of electrons, and charge of electrons. So let's go to the next page. So we say current density, which we denote by J, and we write sub n, because again, we're still talking about electrons, is equal to mobility of electrons times the electric field. Now you can write it as electric field, or you can write it as voltage divided by length. That's up to you. And then we have n, and then we have q. These are all multiplied by each other to give us the current density. And it's important to remember that the unit is amperes per square centimeter. Okay, so it's a little simpler. We don't have to carry the WH everywhere. We just have a simpler equation. That's what we call current density when electrons are carrying the current in response to an electric field or to a voltage. This completely characterizes the drift current in a semiconductor if that semiconductor is primarily N-type. All right, now what if we also have some holes that carry current? Then what happens? Well, all of this analysis applies, except that now we have to switch things around. For example, if you have P-type material, then you have lots of holes. This time we are dealing with mobility of holes, which is different from mobility of electrons. Remember we said in the first lecture that holes do not flow as efficiently or as fast as electrons because they are based on trap and release of electrons. So we have a different equation here, and then depending on the density of holes that are available for current conduction, we have some P, and then of course Q, which is the same thing. So in general, this is what we will see. It's a total current density, which we just write as J, is equal to, we have mu n times Q plus mu P times Q, and then all of this multiplied by the electric field. So this is in general. We have some sort of silicon. It may have lots of holes, very few electrons, or lots of electrons, very few holes, or it may have some electrons and some holes, and they're comparable. In any case, whatever it is, we can write the total current as the current of electrons, for example, going this way, plus the current of holes going this way. Now, the current of holes might be negligible, or the current of electrons might be negligible. That's okay, but whatever it is, that represents the current of electrons, that represents the current of holes. If P is very small compared to N, okay, so you forget this one, or vice versa. But that's the general equation for the drift current. So this is, of course, the drift mechanism. Okay, so that tells us how to calculate the drift current. If I have a certain piece of silicon with some doping or not doping, no doping, doesn't matter. I apply a voltage. In response to that voltage, I have a certain electric field. If I know the amount of doping or the number of free electrons per cubic centimeter, the number of holes per cubic centimeter, and I know these values, then I can do that. By the way, the mobility of holes is equal to, let's see, how much is that? The mobility of holes, I think, is 300 or maybe 400. I think it's about 400 centimeters squared per volt second. I don't quite remember, but something in that range. So it's quite lower than the mobility of electrons. Okay. So we have seen how current is conducted in response to voltage in a semiconductor. Let's now, we are coming to the end of this hour, so I will have to defer the second mechanism, namely diffusion, to the next lecture. In the next lecture we will see how diffusion allows us to carry current. In other words, even if we have no voltage applied, even we have no electric field present in a piece of semiconductor, we could still have current conduction. And that's interesting. That's not something that we have seen in the past. From physics or basic circuits, we always had to apply voltage to have a current. But diffusion is a case where we don't need any voltage or electric field. I will see you next time.